Okay, in this video I'm going to begin exercise 6C of the book Fundamental Applied Mathematics. We're on page number 164 and the question is number 1. So I haven't done a video on Newton's Law of Gravitation. I'm just going to basically tell you that this is the formula here, and what it does is it calculates the force imparted between two different bodies, M1 and M2, when they are distance r away. Capital G is this universal constant, and it's called the gravitational constant, and that doesn't change, and it's just a constant. I suppose for those of you that are big into their mathematics, what Newton would have done is said the following. He would have said that the force between two bodies or with a mass is proportional. He would have said it's proportional to the mass of the body 1 times the mass of the body 2, and it's also proportional to 1 over r squared. So he could have said something like this. He would have said it's proportional to the mass 1, it's proportional to the mass number 2, it's proportional to 1 over r squared. And then he would have said it's proportional to m1, m2 over r squared. And in order to get them equal, you need a constant, so it's f becomes equal to a constant times m1, m2 over r squared. That was a square there. And it's found out experimentally that that constant is the gravitational constant G. Alright, so yeah, the last thing I'd like to say about Newton's law of gravitation before I begin this question is that Newton's law of gravitation falls off, or the force falls off at 1 over r squared. What does that mean? Okay, it means that if you are twice as far away, so say if your force at position x is equal to y, then at position 2x, your force isn't y over 2, it's actually y over 4, because it falls off at the radius squared. Okay, so the distance squared. And this also should tell you that we're talking about radii, so we're talking about circular or spherical volumes. Okay, anyway, let's just begin straight away from here. Not that it is straight away. Anyway, so calculate the acceleration due to gravity at the surface of the moon, correct to 1 decimal place. So the surface of the moon. Okay, calculate the acceleration due to gravity at the surface of the moon, correct to 1 decimal place. So, okay, we have the gravitational constant, we have the radius of the moon, we have the mass of the moon, and we have the mass, we'll say, of anything else. So I'm going to say the m2 is variable. Okay, because it could be anything. Of course, the acceleration due to gravity and the mass, the surface of the moon is going to change. So we're going to get F is equal to, and we're given what the gravitational constant is. It's 6.7 times 10 to the minus 11, not 111, times the mass of the moon, which is 7.4 times 10 to the 22. Okay, times m over the radius of the moon squared. So the radius of the moon is 1.7 times 10 to the 6. We need to square that. So the force due to gravity at the surface of the moon is going to be as follows. Now, by the way, just to point something out, you can actually start adding these powers, but I'm not going to do that today. So 6.7, this button here means times 10 to the, and it's 11. Multiply that by 7.4 times 10 to the 22, and divide that by 1.7 times 10 to the 6 to be squared. And we're going to get that it's 1.71 times the mass. Okay, but we know that the mass, F, is equal to ma, is equal to 1.7 m. Cancel the m's, a is equal to 1.7 meters per second squared. Alright, so basically it's independent of the mass of the body. So thanks for watching, please pass it on to your friends and subscribe to my channel.